This next slide gives you everything you need to know about the binomial distribution. So first off, we derived how to find binomial probabilities. And so that was the number of ways times the probability of a yes raised to the number of yeses times the probability of a no raised to the number of no's. That's called the binomial formula. Now, we computed these, but in real life, you're probably going to be using Excel. So let's go over to Excel for a second. And I will show you how you can make Ed's simple table in Excel. So here's X. Here are the possible values. And here's sum. Now let's find the probabilities of X. We could use that messy choose business, or we could use BinomDist. So let's use BinomDist. Oops. I think I spelled it wrong. BinomDist. Here we go. And you'll see that Excel is giving us some prompts. So the first thing it wants to know is the number of successes. So the number of successes in my table is going to be right here, A15. And the next thing it wants is the number of trials. So trial just means how many times did you execute this experiment. So we did it 4 times. The probability of a success is 0.6. The last one asks if we want a cumulative distribution or just the probability masses. So we don't want cumulative, so type in false here. And that number ought to look familiar. All of these numbers should look familiar. So we need to go one more down. They match exactly what we had in this table. And recall that if you add these up, you should be getting 1. So if we take B15 through B19, they should equal 1. So cool, we got 1. All right, so my point with this is that we don't need this messy formula because Excel will do the messy formula for us. It's doing exactly this formula. Now, the next thing we did was to evaluate the mean number of yeses. So we did this with Ed's simple table back here, and we said that the typical number of yeses is 2.4. Well, we did this with the table, and that's a whole lot of work. Let's see if we can find a shortcut. So the shortcut is given to us on this slide. The mean is just n times pi. So this is a shortcut formula to avoid doing the table. So let's try it on the recall example. If we take n, which was 4, multiply that by 0.6, well, 4 times 0.6 is 2.4, so it looks like it works. And I think that's a whole lot less work than going through the table. The next thing we did was to find the variance. The variance, again, was a whole lot of work using the table. But here's another shortcut, n times pi times 1 minus pi. So let's go over to the scratch pad for a second and multiply that out. So the variance should be equal to n times pi times 1 minus pi, which is going to be 4 times 0.6 times 1 minus 0.6. And this is equal to 0.96. And you'll see that the number that we just worked out equals what we computed with Ed's simple table exactly. So the point is you don't need to use Ed's simple table for a binomial distribution. You have these formulas. Couple more results. Usually we don't care about the number of yeses, and instead we care about the percentage of yeses. So instead of XB, what we want to do is consider a statistic P, the percent of yeses, which will be XB over N. So if you think about it, go back to this first problem. We had 3 yeses out of 4 tries. So P, in that case, is 75%. All right, so instead of talking about 3 yeses, we want to talk about 75% of these 4 responses being yeses. This is a linear combination, And we can use the formulas that we talked about way back earlier in the course packet to derive the following two results from the previous two. So the expected value of p is just pi. So on the average we get, in this case 2.4 yeses. Sometimes we get more, sometimes we get yes, but on the average we get 2.4. And the variance is going to be pi times 1 minus pi over n. So these two formulas are very important to us. The last result I'm going to just state at this point, and then in a subsequent video we'll come back to it in much more detail. So what we'll see is that the distributions of x, b, and p are approximately normal, provided our sample size is large enough. Now, large enough will be defined more precisely in a few slides. This is a very profound result because it's going to mean that we can use the normal distribution to find probabilities rather than this very tedious formula or binom dist. So that's going to save us a whole lot of work. If we look at this this distribution that I graphed, it's n, by the way, is nowhere near large enough at this point to approximate it with a normal, but if you squint a little bit, this thing is vaguely normal. Now if we turn the sample size up to about 15 or 20, it's going to start looking really normal. So that's going to be a very important result for us. So what I've just done is to introduce everything you need to know about the binomial distribution, and that's probably good enough for this video. In a subsequent video, I'll be going through some of these problems with you.